A very good morning to Sir and all my fellow friends. Now I will briefly present the topic again of the column. And this study is truth is the comparison between the critical load of the steel bar and the different type of the cross-section area. So now we can start the presentation. And this our team member including first is Rizan, Izzat, and me who's away as the group leader, and also Abby, and the last is Irfan.
Hi, my name is Muhammad Izzat Adli bin Nissan. My numeric is CD 230 and 219. So my part is introduction. So for introduction, structural and mechanical engineering focus on load bearing safety. Second, buckling in cylinder members like columns in critical to stability. Critical load, maximum compressive load before instability occurs. So the problem statement is steel bars are widely used due to high strength and durability. Second, buckling resistance varies based on cross-sectional shape. Need to identify the most efficient shape under compressive loads. So basically we use and we apply the Euler's buckling theory that PCR critical load equal to pi square EI over KL square. So the E is modulus of elasticity, I is moment of inertia, L is effective length, and K is end condition. So end condition is different based on if you use pin ends, K equal to 1, fixed and free end, K equal to 2, fixed end, K equal to 0.5, and pin and fixed end, K equal to 0.7. That's all for me.
Literature review. The moment of inertia is a property of a shape that shows how well it can resist bending. It depends on the size and shape of the cross-section, and more importantly, on how far the material is distributed from the neutral axis. The further it is, the more resistant the structure is to bending. This is a crucial concept in engineering, especially in the design of beam, shaft, and a column, where maintaining structural integrity under load is essential. First, we have the square cross-section. Its moment of inertia is calculated using the formula I dh power of 3 divided by 12. For a square, both base b and height h are equal. This shape is relatively simple and symmetric, making it efficient in application where load is evenly distributed. Next is the rectangular cross-section. Each moment of inertia differs depending on the axis of bending. The formula is Iz equal to db power of 3 divided by 12 and Iy equal to db power of 3 divided by 12. Here the longest side should ideally be placed vertically to maximize bending resistance. Rectangular beams are widely used in construction for this reason. Moving on the solid circular rod, also called a solid cylinder. Its moment of inertia about the central axis is Iy equal to Iz equal to pi r power of 4 divided by 4. This symmetry is ideal for shaft axles as it offers uniform resistance in all directions and handle torsional load well. Lastly, we have the hollow circular rod or pipe. The formula for moment of inertia is I equal to pi big R power 4 minus small r power 4 divided by 4, where r is the outer radius and small r is the inner radius. This design reduces material usage while still maintaining high resistance to bending and torsion. Why is commonly used in lightweight structural application like bicycle frame and scaffolding.
My name is Mudawina. I present the problem definition part. In this project, we have fixed a significant depth. Our 10-meter steel column has the dimension of the young modulus 200 kilo, and the length is 10 meter, and the bending distance is the 250 meter pascal, while the top and the bottom is two dimension. To compare the four types of the cross-section area, the maximum area of the cross-sectional area includes is the 6cm times 6cm. So the parameter for this certificate is the difference type of the steel column, and the variables is the type of the cross-sectional area. And the full type of the cross-sectional area is a circle root, a circle root, a hollow circle, a square bar, and a rectangle bar.
My name is Muhammad Imran. I will present the mathematical modeling. According to our case study, the principle that we use in the case study for the model will include the moment of inertia, critical buckling load, and critical yield strength. As for the assumption, we assume that the model of the column is made of steel with elastic modulus and yield strength 200 GPa and 250 megapascal, respectively, with length of 10 meter. We also assume that both top and bottom of the column is pin, so the value of the effective length factor is 1. Meanwhile, for the limitation is that we maximize the cross-sectional area, which is 6 cm by 6 cm.
For the result part, the assumption is when before there is the steel and the German models using is the 200 megapascal. The bending stress is 250 megapascal. The length of the column is 10 meter. The width of the with the pin connection, so the plate is equal to 1. The diameter of the root we plan is 6 cm, and the radius of the steel root is 3 cm, so that is convert to the 0.0 meter, and the error we calculate is 2.8274 times power 10 power of negative 3 with the square. So we also to calculate the moment of the inertia by using the formula pi r square pi r 4 pi r power of 4 and over 4. So you can get the moment of inertia is 6.3677 and times 10 power of negative 7 meter power of 4. And the critical root calculate to is the 12.557 kilo Newton. And to checking, we have also to find out the bending stress. There is the critical load over the area. So we can get 4.441 megapascal. And also for the hollow load, we calculate out the moment inertia and the critical load. And finally, we can get 10.077 kilonewton. And to checking, we have to calculate the bending stress. So we can get 6.414 megapascal. And also for the solid square root, because we find out the moment of the inertia, we can get the 1.08 times 10 power of negative 6 meter power of 4. And we also can find the critical load, whereas we can get 21.32 kilonewton. And to checking, we have to calculate the bending stress, and we can get 5.922 megapascal. And also for the rectangle, first we find out the moment of inertia x. Well, we can get 1.35 times 10 power of negative 7 meter power of 4. And also to find out the critical load, as we can get to 2.664 kilonewton. And to checking, we have to calculate the bending stress. That is 1.480 megapascal. And also for calculate the moment of inertia by, then we can get 5.4 times 0 times 10 power of negative 7 meter power of 4, and also the critical load is 10.659 kilonewton, and also the bending stress we get like 5.922 megapascal. And now for the beta part. As we can see the result table, we can know that there's a force shape of the cross section under the circle, square, and the diameter. And for the error, the biggest value we get there is the square 3.6 times 10 power of -3, and the smallest value is the horizontal 1.571 times 10 power of -3. And also for the moment of inertia, the biggest value we get is the 1.08 times 10 power of -6. And the smallest value is to the x-axis that there is 1.35 times 10 power of -7. Next, for the critical load, the biggest value we get is 21.32 kilonewton, and the smallest is the rectangle x-axis. There is 2.664 kilonewton. And when the critical load is higher, the column can support the load is higher. So the ring can support more load between this portion. Okay. And for the bending stress, the highest value against the horizontal 6.214 megapascal, and the smallest is the rectangle. It is 1.48 megapascal. As you see that all the bending stress is here is lower than the mm, lower than the 250 megapascal. So what the result is very.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Akmaifan bin Muhammad Zubir, CD230013. Today I'll be explaining challenge and improvement in cross-section analysis. First, key challenges. Ensuring accuracy moment of inertia I and critical buckling load, PCR. Difficulties with asymmetric shape. For example, rectangles where IX versus IY. Errors from unit conversion to M may affect results. Next is a recommendation. Use simulation tools like ANSYS, SolidWorks, and MATLAB. Maintain consistent SI units throughout. Verify and compare inertias for better buckling analysis. Engineering application and real-world impact. First, applications. Structural design, such as beams and columns. Mechanical components such as shaft and axles. And aerospace and automotive, which needs strength to weight optimization. Real-world use, column design in buildings and bridges. Lightweight structural solutions, buckling and stress failure prevention.
That's all from us. Thanks for your attention to watching. Thank you.